So for this week's seminar, we welcome Professor Tyll Krüger from the Wrocław University of Science Technology, Wrocław Polytechnica, who is a mathematician by training, a long history working in various forms of infectious disease modeling, and of course has been very active in work related to COVID. We got in touch with Tyll through our interaction with the SaxoCove project, which he's also participating in. And so today he's going to be talking about some of his recent work focusing on predictive modeling for COVID-19. So thank you for coming, Tyll. Nice to have you here. The first in-person seminar we've had in about a year, so very exciting.
Right. I mean, thank you very much for the invitation. And for me, it's even longer since the beginning of the epidemics. It's the first time to have an online live seminar, which is partially virtual, but yeah, I see a lot of nice green people here. Anyway, yeah, so my topic is, and the title is a little bit by purpose, provocative, predicting the unpredictable, mathematical models and the COVID-19 pandemic. It's a huge topic, right? So I will be very selective, of course, related to also to closely related to our work and our results. Now, it's not clear what predicting actually mean and what is not predictable, and I will speak about a couple of things, but let me start with the following remarks. So I'm participating in, well, the Ministry of Health recommending strategies since more than a year, and we have weekly meetings. And the politicians always want to know three things: when the next wave starts, when will be the peak, and how high the peak becomes. That is somehow the main thing they are really interested in. You can still maybe differentiate then for deaths and cases, but that's essentially what they would like to know. But that is precisely the thing which is unpredictable, I would say. Right? You hardly get the timing of the beginning of the next wave right. You hardly get the timing of the peak, when the peak really is right. And you also get hardly the height of the peak properly. And there is good reasons for that, because the peak and also the time and the height of the peak very much depend what the state will actually do and when they do, right? And different countries in Europe have different perception what is bad and what is very bad. And usually they react when the things become very bad in their opinion. And that is something a model cannot anticipate, right? So that is hardly something to do. So here you see it's not completely updated, but I think it's illustrative for making my point here. Different forecasts from what's called the German, Polish, European, and the German, Polish, and now it's also European forecast hub, where a lot of teams from different countries, not only European countries, try to make predictions 4 weeks ahead for cases and deaths. Right? Some teams only for the country where they are located, some teams for countries, for all countries, right? The MIT, for instance, makes predictions for most countries in the world. And you see, this, I think, is the German situation. The numbers are accumulated cases per week, right? So it's not the daily incidence, it's the accumulated incidence here. And you see at the beginning, so the beginning of the wave, everybody got it bad, right? They were all undershooting. Then they were all overshooting in the height and the timing when the next week came. And only when the things really don't change, when there somehow is a steady decay, the things becoming relatively good in prediction. And these are the confidence bounds given by the different groups, this columns here, and you see it's pretty huge uncertainty. That is our own predictions for Poland. We only do predictions at the moment for Poland. On the left side, you have the incidences, and on the right side, you have the deaths. And you see the same phenomena, even maybe a little bit less strongly. The mistakes were maybe a little bit less strong than for the German simulations I showed before. But also we have the peak. We have overshooting the peak, and it's hardly get it exactly the turning point around, and it's pretty difficult. So this is here. Let me see, 4 weeks ahead on the right side for the deaths, and for the cases it's 2 weeks ahead, and I would show 4 weeks ahead. The differences would be still much larger. Now, what is nice with this service, this forecast hub service, is actually that you have a little bit in a way how you do weather prediction, a comparison between all the teams which are active in this field, and there is an evaluation done independent of the teams. So they do a relatively quality of the performance, how good the models are. And so you can somehow put yourself also, are there some teams which are much better than you? How good are the predictions? I'm happy to say that for Poland, we are actually in all 8 categories for which they somehow make a ranking. 1 week, 2 weeks, up to 4 weeks, and then the deaths and the cases. On 7 of 8, we are usually on the first place, and then sometimes on the second place. And this is since the last, since it integrated over the whole period. So I'm pretty satisfied with the performance relative to the other group, but we have the same problems as the other ones, that we can't really predict the peaks and the timing when the next wave comes. Good, but there are other things which you can predict. So in predicting the unpredictable, certain things you can predict, right? It's just not that what the politicians usually would like to know, but there are some things still valuable of insights in the cases. And my picture here at the beginning is actually a prediction. It's a prediction how many cases you will have in the country as a function of the quality of contact tracing and testing for a given level of overall restrictions in the population, right? So it's somehow a scan over the parameter space, and it shows you the changes if you would change the parameters. It doesn't tell you where you are, but it tells you what can happen and how this dependence looks like. And you see a very sharp phase transition, and that the things go really high up to levels where you have large fraction of the population infected. So this is, I think, with a certain vaccination level also involved. I just wanted to show that's also a form of prediction. It's just not the predictions you usually think of when you think about weather forecasting, right? Will it rain tomorrow or will it not rain tomorrow, right? These are things which are difficult to predict, but other things you can do better. Now, the second thing is, in my title was mathematical models. And for those of you here at the Institute, which may be not doing actively COVID predictions, I have also made a few slides just of general nature, let me put it that way. Forecasting models, or models which somehow describe epidemic dynamics, infectious epidemic dynamics, essentially split into 2 types of group: the ordinary differential equation system, or the differential equation system league, which is the majority, and they're also the oldest since more than 100 years. First for malaria, they have been established, and they have advantages, and that is where most of the models belong to. The second group is agent-based model, which really do the simulation or the description of the epidemics on an individual level, which allows you to have a lot of heterogeneity built in. You have to also the ability to use more complex parameter sets. But there comes also problems with that, that the computation time is much more harder, and also the fitting of the parameters is much more complex, than in a relatively more simple model where you have better control and also, that's the usual belief, a better theoretical understanding. Good. So the aim of all these models is, of course, predictions as far as you can. A little bit you can do, but it's not perfect. And you have systematic problems and errors which you make. But also what you should do to control the epidemics and what things, what structural factors, what parameters have a strong impact on the course of the epidemics. And for that, it's not just enough to do simulations. For that, you also have to gain some understanding of the epidemic dynamics as it depends, or in its dependence on the relevant features, especially the contact features in the society, right? So this is an important part here to do. Pluses and minuses, ODE versus agent gaze. Well, the ODE are easy to write down, so it's clear what you are doing, easy to simulate, and it's relatively easy to analyze. You know what to do with the differential equation. You can do stationary points and the stability analysis, and this is things you can easily do. Difficult is to add heterogeneity, for instance, in form of distributions. And everything what is easy in the ODE case is difficult in the agent case and vice versa, right? So very natural, you can put distributions of certain parameters in or variables. You can have heterogeneous populations, but the computation and the mathematical analysis is usually difficult, and most people say the mathematical analysis of agent-based model is actually impossible. And actually, I would like somehow to show you that this is not the case. You can do something on the mathematical side. And so, right, this is more or less, I had already, an agent-based model is just a model where the units are individuals and they have features, and depending on the features, the progression of the disease, in case a person gets infected, depends on that, and furthermore, the network who you infect, and depends on your individual features, okay? So all this infectious dynamics takes place on networks. So you somehow have to understand stochastic processes on random networks. That is, for an agent-based model, somehow the ground, the play field on which everything plays out. And the exact structure of the networks is not known. You have to find here some proxies. And then you have within the infected individuals different stages corresponding to different levels of the state of the disease, whether you are in hospital or whether you are staying at home or whether you are quarantined or not quarantined and so on. So that is the very natural, somehow canonical setup for these places. Now, to understand actually the core features of epidemics, I would like to start with remarks which target at the connectivity structure on the networks. And if you come from physics, you know probably pretty well phase transitions in the connectivity structure, which are called percolation models or percolation theory. So this is an old subject. And it turns out actually that you can view an epidemic as a percolation process always. Okay, at least infectious things. And the interesting question, whether an epidemic is overcritical or not overcritical, is you can translate into a question in a percolation question. Now, what is percolation about? So the classical thing is you have like a lattice structure here, and you make edges, you declare edges as open or closed with a certain probability. And so here the red things are the open edges, and you imagine that some liquid comes in either from the top from the left to the right or from the top to the bottom. And you look now how long it will diffuse through this kind of random network structure. And the interesting thing is actually that above a critical probability or likelihood for an edge being open, you have an infinite connected cluster, right? So it means that if it rains on the top, it will go through to the bottom if this structure is sufficiently large. And the same thing you can do with, not on a lattice, you can do it on any graph, right? If you have a network. And here I have depicted 3 different networks, which are just very simple random networks. So between each pair of nodes, you make with a certain probability an edge. And this probability is very much related to this number R, which I wrote here. The R, which gives the mean number of neighbors in these graphs. So the left side is the probability P is chosen in such a way that the mean number of neighbors is 0.9. Okay, so you make random connections in a large group of people, and the mean number of friends you have is a little bit less than 1. And what you see, the graph splits into many small components here. On the middle part, you see if my mean number of friends is 1.2, and what emerges here is the same as in lattice percolation, where you have an infinite connected component. Here we have a finite graph, but it appears a large connected cluster or subgraph here. And if you can now edges accounting for a transmission for something where things can pass along. If you put water somehow in this big cluster in the middle, then every node in this big cluster become wet eventually, right? If you put an infection in the big cluster and this link represents infections, then everybody gets infected here. And the people who are not connected, they are out, they don't get. So to understand epidemic dynamics, you have to understand connectivity structures and sizes of connected components in random networks. Okay. You see, if I just go up a little bit higher, even or equal to, there is just a few isolated nodes and the rest more or less merged into this giant component. This graph was investigated first by the Hungarian mathematicians Erdős and Rényi in the late 50s of the last century. And that's why these networks are called Erdős-Rényi graphs. And what you see here, this little red curve on the left side in my diagram, is the size of this big component which emerges above. Once you have the average degree is larger, in that case, it's larger than 1. And you see it quickly increases, and then eventually everything is member of this large component, right? So, but below that, you have only very small components and they are of logarithmic size. So imported infection will not spread. It will just proportional more or less to the number of imported cases and just constant times that cases you will observe. Good. Now, of course, real networks are a bit more complicated than this type of networks. So you have to look whether you can extend this very nice and very beautiful theory of Erdős and Rényi, on which on the mathematical side, a lot of research activity is going on right today, into more complex networks. And the class we found most appropriate for epidemic processes is a class of network which was first studied in depth from a mathematical point of view by Bolobás, Janssen, Riordan. The class of network itself was invented a few years ago by a physicist, Söderberg, if I correctly remember. He didn't get so far in the mathematical handling. So I named these graphs a little bit Bolobás BGR graphs, according to the people who first thoroughly have studied these things. And the difference now to the previous network, where between each pair of nodes with the same probability you will have an edge, is the following. You give features now to the individuals. So everybody has whatever features you would like to add, age, gender, the education, the profession, whatever you would like to do. And now you make edges between two nodes depending on the features of the individuals, right? So this you just do by defining a function which takes the features of two nodes into account, computes a value out of it. You scale it up by n because you want to have what's called a sparse graph, right? So the real contacts of an individual, the number of relevant contacts is not increasing with the population size, right? So whether you are in a country with 1 million or 10 million or 100 millions, the number of friends remains more or less the same. It doesn't depend on the size n. So that's why you have to divide by n to get the expected number of neighbors or contacts more or less independent of n. This is the setting. And the right side somehow illustrates such a network. You see the colors are the features here. And the red nodes don't connect with the blue ones, right? They somehow don't like each other. And that's why you would not have a connection. And then it's a little bit like an onion structure you can build it. So you can very complex networks build, which are now not as homogeneous as the previous one, just because edges depend on features. But there's one important mathematical aspect which you keep from the Erdős-Rényi model, and that is the independence. So also the probability of an edge depends on the features. Whether you have an edge between two individuals has no impact whether between another pair of individuals there is an edge, right? So there are independent events. The probabilities depend on are individual dependent, but the edges itself are not dependent on each other, right? So this is the key mathematical feature which allows you essentially to go further with the analysis. Good. So you can assign a lot of features, and that is the nice thing also what we do in our modeling here. The whole thing which you have in the microcensus and you think it matters for the epidemics, you can put somehow in the household size, the work status, even the time being infectious, which is something which you can actually a priori gamble out. So it's you can assign it as a feature of the individual, right? Once you get infected, the likely progression of your disease depends on your characterizations, age, gender, comorbidities, and so on. But it doesn't depend on the rest of the epidemics so much, right? The time till quarantine depends whether you will be found, whether you go to the doctor. But again, this depends more or less, it's something you can a priori decide. So it's, with some exceptions, many of the progression of the disease, you can a priori already inscribe into the feature vector of an individual, okay? So you don't have it, because they don't depend on the whole epidemics, they are just in individual property, a random property. So you can gamble it out and put it into the feature vector. Whether you go to the hospital, whether you don't go to the hospital, once the hospitals are not yet full, which depends on the whole epidemics, this you can do. Good. A couple of things you can't do, but a lot of things you can do. Now, how does graphs look like? And actually, the local structure here, I put a little bit the math in, so you have how to describe but the best is you look maybe on the right picture, because this is how these networks locally look like, okay? They look like trees. If I ignore for the moment the households don't look like trees because you all know this, but outside the household, so the network structure is locally a tree. And that's why this structure on the right side, you can mathematically formulate or describe as a multi-type branching process, right? A process which generates a random tree by saying how likely is that a person will now create offsprings where the arrows go, and what is the distribution, and how many offsprings I create depends on my features. Okay, so it's a multi-type branching process, and this describes the local structure of this network, not the global structure, which is not a tree, but the local structure is a tree. Good. I want to mention here also that the theory of Bolle-Janssen-Riordan is usually assuming that this kernel, which describes the probability of an edge, is symmetric, so it's not directed. But there is an extension of this theory to directed links, and then I would make an arrow from I to j, and which I interpret later on that this arrow is, which I interpret that if node I would be infected, he would infect node j. So an edge stands for a realized infection process. Okay. Good. So this is the local structure, and you can describe now nicely somehow the mean number, for instance, of neighbors I have, depending on what type I am. You just have to integrate here over this over the kernel. And the features themselves have a distribution. So mu is the distribution of the features I assume in my population. Okay, it can be very complex, and because the feature itself is a vector. Okay. Good. Now, the key mathematical object on which you have to look is the so-called transfer operator, which somehow describes what's going on if you go from one level in this tree, from one generation to the next one. So assume you have what's written here. This integral is essentially the following. I have a node X, say this big blue one and on the top here. And but the contacts he has is not is selective. He doesn't have contacts with everybody with equally likelihood, right? So if colors are the features, he has a preference to these green ones and to this brown one and the other ones. And now I have a distribution on a function f on the population. But what I'm now interested is the weighted mean, which the weights coming by the likelihood that this individual blue or the individual X here is making an edge to this thing, right? So I weight the population. I have a certain distribution in the population, but I weighted now this function with the likelihood that I will make an edge to a person, right? So if I don't like a certain group of people, I don't make contacts, this node doesn't contribute in the weights here. So it's a weighted average here. But this operator describes somehow the process. So now you can iterate it, right? You go from one level to the next level. And that's why the norm of this operator is actually what you call the reproduction number, right? So usually if you write down the reproduction number in a complex situation, you get a little bit of hand waving. The mean number of secondary cases, assuming that all your contacts were not infected, right? This is somehow the textbook. But the problem is, what is the mean here really? And when you take the mean. So this is now a precise, and it's also the accepted. So it's not my invention here, right? So this is already standard. The norm of this operator is, can you interpret as the mean number of offsprings generated once this process somehow stabilized, right? So you let it, of course, depending where you start, at the beginning, these trees look very different. But once you do a couple of steps, but not so many steps that you see already the whole population, then you end up with somehow a regular growth from generation to generation. And this mean out degree here from one level to the next level, this is the reproduction number. And this is precisely the norm of this operator. And if the graph is not symmetric, it's actually the spectral norm, not the L2 norm. Okay. Now, the nice thing is, once you have this linear operator, you can write down an equation and say, and compute out of this equation the likelihood that a person with a given specification of its features will eventually become infected if you have an overcritical epidemic. So you have this huge giant component. And this is this equation here, which in the Erdős-Rényi classical case is just every individual is equal. So just rho equals 1 minus e to the minus mean number of neighbors times rho. And here it's a little bit more complicated because you have an integral operator in the exponent, but it's very easy numerically to solve this equation. The right side is a contraction. So if you start with 1, with the constant function 1, and just iterate it, it converges very quickly, exponentially fast to the solution. Good. So you can get, and then you can integrate over this likelihood, and then you get how many people get eventually infected. So it's an explicit formula. Even if you add 1,000 of features to your individual here, okay? Assuming that the rules for forming the networks don't depend on time. And it also doesn't tell me how long it takes till this happens. It just takes at the end, right? So once at the end of the day, the end of the epidemics, we have this fraction of people infected. So for the non-symmetric case, we have the spectral norm here, and I summarized a little bit up. Giant component, supercritical epidemics. This norm is larger one. Norm less than 1, many small disconnected components, subcritical, and for norm equal to 1, you have exactly the phase transition. Good. So in this understanding and also predicting epidemics means from my side very much understanding how this norm, the spectral norm, depends on the features on which you have control or on features which are maybe country specific, okay? And medical interventions, social structure, social economic structure. Good. Now, there is, for this number of infected, still one thing to say if you deal with directed things, which is maybe a little bit technical, but I would like to make one point out of this, which is then probably not too technical. So in a directed network, you can now look from starting from an individual, you can look forward in the direction of the arrows. And locally, this is a tree. Okay, that's all what I said is true. Now, but you can also reverse time. I'm an individual, but I look now against the direction of the arrows, right? So it's like in epidemics, I can look, I'm infected, I look who I will infect, and then I look who they will infect, and so on. I can also say I'm not infected, I look who eventually would infect me. And from those people, I can go one step further, who would infect those people eventually. That is just going backward in this network. And I have 2 different branching processes, 2 different tree structures, depending on whether I look against the arrows or whether I look in the direction of the arrows. Now, they are, of course, because they're coming from the same graph structure, they have something in common. And the common thing they have is that the transfer operators describing the forward picture and the backward pictures are just the adjoint operators. So physicists know what adjoint operators means. You have this integral and you exchange the variables in the integral here. And adjoint operators have the same norm. So the phase transition is the same. But the structure is really different, right? Imagine you have a process where you have two types of infected. One type always generates exactly one secondary case, and the other type generates 10 secondary cases. No other numbers appear. But they somehow do it randomly. They choose, the one person chooses one random and the other one 10 person at random who he will infect. Now, from the perspective of the person who is not yet infected or somehow eventually becomes infected, you look for the possible incoming edges. And what you see here is just that that I'm essentially like in an Erdős-Rényi graph. I have a distribution of incoming edges, and the probability, because I get chosen, it's just like a graph if it has a constant probability to get infected. I could get from everybody infected. Okay, so it's they can be look very different. And as a general message, and that I think not many people have really also in epidemics well understood, at least in applied epidemics. I think in the mathematical community this is understood. But is the following. People worry sometimes about what is the impact of certain heterogeneities in features. For instance, I have time varying infectivity. Infectivity is not constant. Or I have super spreaders. I have some people who infect many because they have a high virus load, and some other people have a small virus load. As long as they don't, this creates new correlations. So as long as the people who the super spreader infect are just normal people and not again just super spreaders, or as long as the person who has a high virus load, he generates just randomly high-low virus load people, then the backward process somehow doesn't see this kind of differences. He just sees the mean value. But this backward process is usually much, much simpler. And that also means for the question of the phase transition and also for the number of cases you eventually get, it's irrelevant to look at these quantities. But it's relevant for certain dynamical features. It's not that it doesn't matter, but for key features like the phase transition and the eventually number of cases you get infected, it's not relevant. And so usually this backward picture is a simpler process in many cases than the forward picture. But they contain the same information essentially, right? So here's the super spreader event, super spreading somehow. The forward structure is complicated. You would have a feature in the population, and some people have distributed, say, according to a power law, and some people generate a lot of people and a lot of secondary cases. But then you look at the likelihood to get eventually infected, and you see that this likelihood doesn't depend on the details of the distribution of your super spreading feature, right? So social activity or whatever it is, but only on the mean value, right? So it doesn't matter the distribution here. You can just assume the population has more or less an average number of infection produced, but it's not depending on the details. Good. So this is differences forward and backwards. It's one of the things you have to understand. Now, I would like to come to one of my favorite topics, which is households. And I will maybe a little bit shorter than in a recent talk I speak about that, but households really make a heterogeneity which you can't discuss away. So it's not like the super spreading stuff. The households create a correlation. And the reason for that is very, very simple. So here
a network without households, then you make now group people together, these dashed lines, and I make little bubbles, and that are the people living together. And now I shrink the people living in a household into one node and get a graph representing the network of households. And actually, you should look as an epidemics as an epidemics between households. Households as kind of supernodes, right, which have a complex intrinsic structure, but they infect other households. And there is a process going on in the household, which represents the infection there. Now, the point is that the likelihood, say, of a connection between two households is proportional to the product of the sizes of the households. It just follows from the fact that as more if I have 3 households member in the one group, 4 in the other one, the number of possibilities I have is just proportional to the product of the sizes. For each possible pair, I have a probability that there is a connection, that they know each other. So the total probability that this household has a contact with this household goes proportional to the product of the household sizes. That is the key observation here. But this product is coupling is actually now really not what, as I discussed before, where I just randomly say, in fact, people in the super spreading, I have preferences, right? So large household preferentially have contacts with large households. Just by the combinatorics. It's nothing social I have to assume here. It's just coming out from the plain combinatorics of the number of possibilities. Okay. Now let's assume for the outside household a relatively simple structure. It can be generalized, but I don't make it here too complex. Just a very homogeneous Erdős-Rényi graph, just to see where we end up when we do a random network at the beginning. So for the out household contacts, I have a constant probability, a small one, so that my mean number of out household contacts is a constant, C. And it's Poisson distributed. And then I now put households. I put nodes in the household. Let's see what I'm getting in the final network here, and how I actually go on and describe now the same thing as before, this tree or local structure for the household graph. And I still have to make an assumption on the household attack rate. So if a household of size K gets infected, then the expected number of remaining household member which still get infected is just K-1 times this attack rate. So it just the expected number of cases which still get in the household once an infection comes in. And UK is the distribution of the household size, the fractions household of size K. So, and now the equation 2 here, this is now the coupling, the kernel, which describes the probability between a contact between two households. But I speak here about infectious contacts, right? So that's why the one household, the X household, has to have one infection in, and that's why there's a 1 here written, right? There's 1 plus 8 HH. So I need at least 1 infected in the household. I won't allow to expect what is the likelihood that he will infect a household of size Y. Y's are now integers, 1, 2, 3, and so on. And this kernel here, divided by the total number of households, gives me the likelihood that a household of size X, an infected household of size X, will infect a household of size Y. Okay, if this is my attack rate. That there is the capital E coming in here, it's just because the household number of households is smaller than the number of individuals. And this requires some rescaling of the population, and that's why you have to divide by E. And C is the mean number of out household contacts. Now, with this kernel here, you can now write down the so-called transfer operator. And now you can compute the norm. And this is just a non-symmetric linear rank 1 operator. And it's very easy to compute the norm here. And that's what equation 5 gives. So this is the mean household reproduction number, right? So it's not the individual reproduction number, it's the household reproduction number. How many households? A typical infected household, how many secondary households you will infect? And you see, C is how many on the individual level, how many I will infect out household people via out household contact, that's C, but there is a boost. There is something coming in which enlarges this C value, depending on the attack rate and depending on the ratio of the second moment, so the mean squared of the household sizes divided by the expected household size, right? So this is what you get out here from the math. Now, this whole term you could somehow interpret as the boost factor due to the households, right? But it's the household reproduction number, not the individual reproduction number. But still, this number has to be less than 1 to prevent an epidemic outbreak. If this number is larger 1, you go off. So C could be actually less than 1. The mean number of out households, in fact, secondary cases is less than 1, but this boost can be large if they have an unfavorable household size distribution and you get an overcritical epidemics. So let's look a little bit what the reality looks like. For Poland, well, taking here really data which are more than what Eurostat has from the GUS, you get actually a pretty large quotient here for the second moment via first one. And that means that the boost factor, so just what's here in this bracket, right? Remember, C is the mean number of secondary cases outside the household, what we usually call the R. This gets now multiplied by a factor 1.65. So the Polish households, right? If Poland would be a single population, the real household structure in Poland would somehow increase the risk of an epidemics by 65%, right? It would boost whatever your reproduction number outside the household is by 1.65, so 65% increase. It's the same effect. The Polish household structure has the same effect as the British variant, you can see. The German thing is much better. It's only 35%, so it's half, right? And that is, you have to understand to see that Poland has a problem with certain things which Germany doesn't have. Okay. Let's look a little bit for our country. So here it's Poland still. This here is just the second moment, but the quotient is also a little bit similar. So these are the regions where you have heavy tail, large households. And anyway, so I looked a little bit because this formula is the household reproduction number. You would somehow think for countries where this factor is larger, the prediction somehow, the perspective of the epidemic should be in tendency a little bit worse. Now, how I measure how good or how bad the epidemics went in a country, the right thing is, of course, to look at the number of cases you have in the country. But the true number, I don't know. The only good statistics I have is the deaths. So I take the deaths and not just the official COVID deaths, I take the whole excess death as a proxy, a very rough proxy for the number of cases. More or less, you can think one death before we had the vaccination. This is somehow for up to end of April. So this is the epidemic situation until that middle of April. It's a rough thing. It depends still on the age distribution in the country, but just as a first somehow try to see a possible relation, we plotted here what the different countries have as excess deaths. You could somehow, if you multiply it by 100, the figures would correspond to percentage of the population infected. So Germany here has, with this method, about 11%. The Netherlands has 12%, maybe. Poland has something like 30%, right? So this is just from the plain extrapolation of the axis that the true numbers deviate a little bit from that. But you see, these are all countries larger than 12 million people with population larger than 12 million, because you have a gap between 12 and 17. So they are all put here together. If smaller countries deviate more, but I find it already quite remarkable that you have such a kind of seemingly, I mean, in a correlation, it's not so bad, right? So if you come from biology, this would say is a very good correlation. Okay. Now, this is something how we estimated really the dark figure now with age things, and you can do it. I will skip this because I have a little bit, yeah, so that's not running too quickly out of time. Good, but of course we know it's not just the household factor. It's also the out-household reproduction number, which is, in essence, a measure on how much you restricted the epidemics. Because what I showed you before actually doesn't depend so much, this computation doesn't depend on the assumption that I have a Poisson distribution with a constant value of out-household reproduction numbers. It can be any distribution. It just assumes that is now this forward-backwards trick, that it's not targeted. So you can have a very, very inhomogeneous distribution on how many people a person would outside his household infect, if he is infected, but it's not targeted to some specific types of people, which again, there is no correlation between my reproduction number and the reproduction number you have if I infect you, okay? The out-household reproduction. If this is the case, you can still, of course, see the out-household reproduction also as an average measure for how good the restrictions have been in a country. Because if this out-household reproduction is small, that means you were not allowed to have many contacts. If it's less large, they gave you a lot of freedom to infect people, and that you should somehow see. So now, can you do this, deviate this out? And here comes a little computation which I want to show. Assuming that we have just single households, and alpha is the fraction of infection in the population, every individual now has an individual reproduction number CI, and the C is just the mean of this individual reproduction numbers. The people are to different times infected, and they have very different, depending on the restrictions, whether they contact traced, whether they were quarantined or not, whether they went to the hospital, they have a different number of secondary cases in general, right? Everybody has, at the end, every infected has such a number. I don't make any assumptions on this distribution. I only assume that the people I infect have their CI value independent of me, okay? Good, and C is now the average. What is the probability P that an individual gets infected? Clearly, this is equal to alpha, the fraction of infected in the population, but I can also do it in a different way. I can compute now the likelihood that none of the other individuals, so actually element I should say I-1, I have a test individual, so I'm not considering it, but that doesn't really matter really. So 1 minus C divided by S, CI divided by N is the likelihood that individual I will not infect me. He infects CI people, it's maybe 10, but I'm not the one who is infected. And I have everybody, so if to get not infected, that is the product term, none of the infected should infect me. So I have to multiply this probability. And 1 minus this is then the probability that I get infected. And then you do a little bit the math and you get this equation 9. And the P is actually the alpha in that case. And that is just the equation of the Erdős-Rényi giant component also, the relation between the giant component and the mean number of contacts I have. It doesn't matter, even in the directed case, it doesn't matter that the out degree distribution, what is the distribution, only the in degree matters. And this is Poisson then, but the out degree can be any distribution. So it's the same equation. And now the question is, can this relation between household, between the number of contacts and the prevalence, how to modify this in the household case? This is a little bit complicated, so I just showed the result. This equation here is somehow the equivalent to equation 9, which would read alpha equal 1 minus exponent alpha minus c, in the case for Germany, if I make a cutoff at households of size 5. So this is how do you have what you have to compute to take the households now in. It's a little bit lengthy, a little bit combinatorics. I don't want to bring you through, but what you see here now is the following. On the x-axis, you have the mean out household reproduction number integrated over the whole epidemics. On the y-axis, the fraction of individuals which got infected. Okay. This is now showing the relation between these two quantities, fraction of infected in the population and the out household reproduction number. The green curve is Poland and the black one is Germany. So Germany, the phase transition for Germany, this little wiggle at the things is just a numerical instability. I didn't make a higher resolution here. So around between 0.78, 0.77 is the phase transition in Germany. If you are below that, there is no epidemics. If you would be below that, there would be no epidemics. But Poland, when Germany hadn't even started to make epidemics, would be already close to 30% of infections, with the same mean number of secondary cases produced by a typical infected outside his own households. So Poland is here really bad off somehow. and it's a big gap, right? And so at the moment, we estimate for Poland actually 45 to 50% of the population already infected. And you see Germany with the same restrictions would much, much lower here, right? So this is a structural difference between the two countries, which you actually only understand if you really do the math. The theory becomes here really crucial. And then you can still look how it's modified by more fine structure by a simulation. So here I compared the countries, somehow 3 countries, numerically still to make in a table. So the estimated by end of April, the estimated prevalence in Poland is 45. It is now accounting for age differences also. That's why the numbers gets higher. And Germany has 12%, and we estimated here for Great Britain, 30% of the population have had already COVID. The dark factor is here written in, so it's in relatively high in Germany. It's for integrated over the whole epidemics, right? So it's not the actually dark figure number, it's the overall situation, and that are the estimated out household reproduction numbers. But what you see now, and is if I would switch somehow the populations between Poland and Germany, but stay safe for Germany with the same restrictions we had here, where the mean out household reproduction number is a measure for the mean restrictions we had over the whole course of the epidemics. Then for my 12%, just to exchanging Polish household structures now, getting the Polish household, I would match up to 38%. So a big jump in the number of cases. If we would do exactly the same, of course, we would not do exactly the same because you would see the cases rise up, you probably would earlier react. So it's a hypothetical game. But if with the same restrictions we had in action, which affect in the same out household reproduction number, Germany would get much, much more, 3 times as much infected. If you switch just the out household case, so from the 0.83 to the 0.89 from Poland and give it to Germany, so a little bit lesser overall restrictions than we had in Germany, there would still be an increase from 12 to 22%, but not as big as the household structure. So you see both is important. But the household somehow is even the dominating effect here. And you can then still do a little bit this game between the other countries. Great Britain and Poland is pretty much exchangeable. So that is the attempt to understand a little bit this picture here, right? So this is the stringency index. And the idea was here somehow to come up with a more mathematically founded quantity, which somehow also doesn't see the timeline, but see the integral under this curve somehow. So that was somehow the idea. Good. Now, there is still a couple of other things. Prevalences depend now on household size. So for instance, the population has now not equal fraction of infected in the different. If we divide the population in those who live in single households, two households, and so on, we get now an inequality in this prevalence. How large is the fraction of infected in these different groups? You see in Poland, single households only 33%, but the 56% by the larger household. But it means also it gives you now a little bit stronger protection against the next epidemics, because you have so large part of this somehow like they are burned out already, right? These parts which were the driving forces for when you still didn't have so large numbers are now somehow you burned out the fuel we have for the further epidemics. That's why Poland is, despite much lesser vaccination effort than in Germany, is still at the edge of the criticality right now because of this additional effects which come here. And this is a German company, it's only to households of size 5. Now, this is the math. I will skip about this. Similar effects, vaccination also you can involve here. You can compute the households kernels and see how the effect is. Interestingly, the household effect again makes the vaccination stronger than you would expect in a single population, right? In a single population, you would just see if V is the fraction of vaccinated, so 1 minus V is still the likelihood to meet a non-vaccinated. So this goes in as a damping factor on my household reproduction number. If I have 50% of the population vaccinated, only every second previously infectious contact is now infectious because half of them are vaccinated. But you see, it comes again in the inside the household. So you have somehow a double effect, and you compare Poland and Germany, the red and the green line here. You see that this out-household reproduction number, if the vaccination goes to a high level, they become more or less the same, and the household structure diminishes to show up their importance. Okay, good. So that's about the households and the children. I want to come still about timing and say maybe 5 minutes speak about timing here. This more all structural consideration. Nothing about the timing. I was thinking in generations. I infect a group of people, they infect the next, but I didn't care when it happens. So let's look now a little bit what the real time process going on. So, and this is actually, again, a percolation problem, but this is now called first passage percolation. First passage percolation adds additional to the classical percolation model, still a travel time along the edge. So think of water sipping in, but it takes now a little bit time to go through one of these edges. And this random tau ij is just the time the water or the infection would need to travel from node I to node j. So in epidemics, it's just called the generation time, right? So the individual generation time, I infect 3 people, how long it takes from the time when I got infected to the moment those 3 people got infected. They have all 3 different times, but this is a random number. And this time is precisely the travel time of the infection from me to the next person in which I will infect. Okay? So now we assign now to the edges this kind of generation times. Here comes the time dependence of the infectivity, the incubation time distribution. All the things come here now in, right? Previously they were absent. It's just whether I infect, with how many people I infect, but the timing now comes here in. Good. Now, what is the branching picture is still true. but now we have the edges equipped with time. So I can speak now also except instead of the generation, right? This growth of trees from generation, first generation, second generation, third generation. I can now go in real time how this growth of the infection will go on in real time. And I take maybe the single case, it's a Gordon-Watson process, so a single type thing here, and you have this lifetime distribution, phi on the edges. And this is well-established math in more than 50 years, that the growth rate of the number of cases in real time in this branching process, in a simple branching process, is given by what's called the Malthusian parameter, which is A, and it depends on features of your distribution on this travel time, okay, and of course, the mean number of secondary cases, right? So, and the following equation, equation 9 is the important thing. M is the mean number of secondary cases I produce. In the household case, it would be the spectral norm of the households, right? So in our cases, it would be just the out household reproduction number. A is the Malthusian growth rate I would know, how the epidemics really grows in real time. And phi is the distribution of my generation times, the travel times. And then I take the Laplace transform of that, multiply it by m and equate it to 1. And that solution is the growth that describes me how the growth rate depends on the reproduction. And what people usually do, which coming from ODEs, they work in example 1. They have exponential times mostly. And that is the relation, a very simple one, of the growth rate. So it's proportional to lambda as so this is the 1 over lambda is the time, the generation time. If lambda is very small, generation time becomes very large. It takes a long time till I infect the next individual. So if as smaller lambda becomes, as faster the epidemic goes, as larger lambda becomes, it goes, and it's proportional to n. If I have a gamma distribution, the dependence on the reproduction number of the real growth rate is a different one. It's the kth root. And if I have a uniform distribution, it's still a more complicated expression. And if I have almost peaked or somehow localized distribution, then it's just logarithmically going with the reproduction number. And that is important to understand if you want to understand how elastically changes, for instance, in my reproduction number imposed by losing restrictions or imposing restrictions have an impact on the growth rate. Okay? So this kind of things are important here. This is all a more or less classical theory. You can extend it to the multiplied setting. It becomes a little bit more complicated, but you can now make also this travel times feature dependent, and then you somehow get the math here is still standard. I think this is all relatively, all more or less completely known. There's nothing our own contribution, it's just a sum up. But this result now is new, and it's an extension of a result which was previously obtained for a much simpler class of random graphs. And actually it tells you that the whole shape of the epidemics essentially depends only on features, on some features on two random variables. One is coming from the forward branching process, one coming for the backward branching process, and a Gumbel distribution. And essentially also that the timing of the peak, I mean, this is the ln, let me put it that way. What is ln? So you pick up at random two individuals, okay? And you ask, what is the distance in time now from between these two individuals, which means the following. Individual I infect how long it takes if the epidemics doesn't die out, that individual G will get infected if the epidemic starts in individual I. This is a distribution. It's not a quantity. First of all, it's relatively strongly localized because this timing is somehow concentrated around log n divided by the Malthusian parameter. And the distribution is somehow a universal, it's somehow like almost an explicit solution of this differential equations is usually fly down. Of course, it's not explicitly the W plus and the W minus. It's a convolution. It's a limiting convolution which shows up in the branching process. That all the complexity is in that in. But it's just the sum of three random variables which describe here this kind of things. And having this theorem, and this is not an easy theorem. This is somehow you really have to quite a lot of work. I thought I had it here in the reference given. Anyway, with this in mind, you can now, for instance, come up with an equation once you have simulated in population and you don't know the dark figure really, and the fraction of the immune people, and you want to change these two things, and you would like somehow to compare the peak height between two things. You don't have to compute the second times. You can use now the theorem and somehow estimate it. And that actually works. I mean, even knowing the shape here, just, I mean, this kind of nice things which somehow offers you by some math. Good. So we do a lot of this math, but we do a lot of other things. And I just wanted to show you our standard stuff here. This is all the machine, the computing stuff and the ECU. You put a lot of these heat maps. We produce phase transition with vaccinations as depending on the contact tracing and the testing levels. And this is our forecasts on our page, which are always a little bit updated here regularly. Actually, I didn't update this picture. And the data we have used in Poland were actually pretty interesting. We really had tree-like structures between the infected patients. And so this is all activities I didn't speak today about. I also didn't speak about the mathematical theory of contact tracing, which is interesting in itself. But that is another talk, I would say. Today, I would like leave you these two key messages. First, agent-based models, you can do a lot of math. It's not just that you cannot do anything, but people from physics, particle system, interacting particles know that you can do this. There is a very often heterogeneity smooth out when you're only interested in phase transitions and prevalences, and because the backward process is the relevant, so where you look against the flow of the infection, and this somehow makes the things easier, the expectation mostly come in, but the household structure is something which is really inducing a correlation in your network where the variance of household size via the second moment enters in. And if you can have random variables theoretically where the expectation is finite, but the second moment is infinite. And in that case, you would not have a phase transition at all. Of course, we don't have infinite household sizes. But it's also interesting because in statistical books, usually, or in the documentations, they make a cut off for households at a given size, because who's interested in these few households larger than size 10? But the tail here, the second moment, really depends very much on this big household. They have a very important role in the initial boosting of the epidemics to play here. So vaccinating according to household sizes would be a recommended strategy. I didn't have time to show analytic results on that, but this is certainly something you can do. And I think it's one of the really most dominant structural impact factors in this epidemics. And big differences in European countries are probably not entirely, but to a good part due to differences in this household structure. So that's maybe for today. I had here some picture where I had, yeah, here I have it actually. Good. So mostly the Martin Bodek and Tomasz Żonański do almost all of the simulations here. And our people are a little bit in data, and it looks a little bit bigger than we really are, right? So these are people which also at different times have contributed here. But some we have data discussions or things like that. Piotr Szymanski is for mobility relevant. Przemysław Becek has done a lot of individual-based death rates and likelihood to go into the hospital done. Is in Warsaw. Anya Gambin, well, I just did something with her on waning of vaccination and impact of passport holders. It's a lot of people here. Not everybody is equally involved. Barbara Papian is our social scientist, and Agata is responsible for the sample population. So Viktor Bezborodov, that's the person I do the math with. And Marek Braviec is for the parallel computation relevant. So it's a bit the group structure. Thank you very much.